Please, to introduce yourself.
I am Germano, and I am an Italian PhD student, and I stay here up to the end of the September, and my topic is about wind simulation. And in this week, in this last month, I collaborate with Simon because our topic have some stuff in common, and so we present our pipeline for our work.
Thank you very much, Nicola. Also, warm welcome from my side. As already said, I'm Simon, and I will be mainly, I will take the second part in this presentation, which will be then an application where we simulate two fluid flows in the natural and built environment. This was the topic of my master thesis. The final aim was to simulate free surface two fluid flow in mountain torrents, where we wanted to investigate also structures in the field of hydraulic engineering. Thus being said, we start into the geodata processing pipeline, which is more or less our common basis for our two applications, the wind simulations and the free surface flow application.
So in this coffee talk, we want to explain our general pipeline for geodata processing, and the pipeline is a modular setup to be applied for different purposes. For example, for wind simulation, for water simulation. So we split the presentation in two parts, and so in the first part we explain the functionalities of our pipelines. And we will talk about the procedure to generate a model with the terrain and buildings that can be used to perform a wind analysis. At the beginning we have two different data sets. One about the buildings, one about the terrain. After we combine these two different sources of spatial information to generate a body-fitted numerical mesh, and we use this numerical domain to simulate large-scale geophysical flow. Here we have an example about the preprocessor, because we can need to have operation on geophysical on geodata files. So with our preprocessor, we can manipulate our files. For example, we can cut a rectangular region or a circular region. We can also extract just the mountains or the rivers, and we can shift the coordinates and so on. So after this process, we have a situation like this. We have a point cloud, and these clouds can be an XYZ file or an SQL file, an OBJ file, and the list can be extended. So with these point clouds, we compute our first 2D mesh with the triangle library that is included in Kratos. And after all this mesh, we can compute a volume extrusion with the TETGen from mesh file library. And so here we have a first 3D mesh that is very ugly. And to do this, we needed the three markers. One for the bottom, one for the lateral surface, and one for the top. So we use these three markers into TETGen to generate our first volume mesh. And the next step is to improve our mesh quality, and we have a computational distance field from the ground. And starting from distance field, we can perform a metric-based remeshing, and we obtain an egg quality, and we can repeat these steps to improve the quality. So the process is iterative. After we added the information about the buildings and the geometry of the buildings can be imported with an STL file, a WJ file, GML file, and also in this case we can extend this list. And here we compute the distance field from 0 level on building surface in this case. And this is FE and the robust with the variational distance process. And here we use the distance field for metric basic remeshing, and we have small elements where the geometry has sharp corners. So here we have a nice number of elements, and we have an exact representation of the distance field. To do this operation, we use the MMG library, also in Kratos.
Excuse me, when you say that you have an exact representation, what do you mean? Is it a representation of which distance? The distance to the surface of the object?
And around the building.
So you put the nodes on the zero surface here.
Yeah.
Not yet. The nodes will be put on the zero surface in the next step.
So weight is exact.
Here we only need a mesh which is fine enough to capture the distance field of the building hull, because you can imagine that in a very coarse mesh you cannot capture the exact distance field. So this is a preparation step.
Okay, so it's not exact, it is accurate, let's say.
It's more accurate than it would be on a coarse mesh.
Okay.
I'm sorry, and what is this variational approach to this? Can you explain a little bit more? When you say it's a variational approach, what is that mean?
Is the variational distance process.
Exactly.
Of Kratos.
Okay. So I think it's related to the iconal equation that is solved in a variational approach in this case.
Okay.
And the last step is to compute the isosurface discretization. And here the nodes are positioned on zero isosurface of the distance field. And the elements with the negative distance value are deleted. So here we have new condition, and so new conditions are created here. And the number of elements is reduced, but without the loss of quality and precision. We need to extend this approach at the level of the whole town, but we know that the geodata sets are limited precision, so it can be happen that the building geometry overlap, like in the left side. And our robustness investigation showed that this is not a problem for our pipeline. And here we have an example also that with a cut of the buildings from the boundary, the domain boundary, and we haven't a problem about this. And here we have another example with two buildings that are very close, and in the left side, and one with an offset from the ground on the right side. And also in this case we have a problem about this issue. We opened an issue on GitHub named Proposal of External Application. And this is the work process that we just been explaining. So we invite you to discuss possible features. Okay. Now here we explain the steps to have a model for a wind simulation. And first of all, we need the information about the terrain from a digital elevation model. And so after this import, we need to cut a circular region. And so with the circular region, we divided this area into three parts. In the inner circle, describe the real orography where the buildings are placed, and in the middle angular zone, describe the real orography without the buildings, and the outer circle is subjected to a smoothing procedure, and the models simplify orography. And a geometry like this avoid discontinuity in the incoming wind velocity profile. So after this operation, we can generate a tetrahedral mesh of the cylindric volume, and here we have the terrain surface on the bottom, and a flat surface on the top. And about the buildings component, we import the data from OpenStreetMap, which is a global database with free data. And in this OpenStreetMap file, we have some geometries that are not necessary in our topic, like in the picture on the top. So we need to extract only the geometry about the buildings, but after this step we have another problem, and we have all the buildings on the same plane with z equals 0. So we needed to shift these buildings on the terrain, and to do this we use the function into graphs. And at the moment, the part about this topic is in this situation. We have a volume mesh with the buildings on the terrain, and in the future we will use this model to compute a wind simulation.
Excuse me, one thing. You said at the very beginning that you have marker 1, 2, and 3 for top, sides.
Yes.
So finally, what marker are you applying on the surface of the object? This was an open question, I think.
Sorry.
At the beginning, you were showing we have different markers,
Yes.
which are needed to comply boundary conditions. We say. Are you regenerating, assigning a marker to the surface of the object?
I assigned this marker in the marker 1, for example, is for the terrain surface.
Correct. But what is on the red surface there? So what the equivalent of it on the volume mesh? Are you assigning? Are you identifying it somehow? Not yet.
No, unfortunately not yet. The huge problem is that we've still experienced several problems with the MMG library concerning the conditions, so that they're at the moment all vanishing and they're being recreated. So at the moment we haven't got the option to maintain knowledge about which condition has been generated out of which predecessor, and we cannot trace back which of the finally existing conditions has belonged to which former domain part.
So the markers are not maintained?
No, it is not. unfortunately not through the MMG process.
But the problem is of the MMG, or is it of our process, on how we handle?
I think it's at the moment, the main problem is personally, from my perspective, my limited knowledge about MMG, that we are getting weird errors concerning null pointers to non-existing conditions, and I think it's a purely technical issue which can be solved, but where our knowledge is not sufficient at the moment to solve it right now. That's why this remains still open, and so at the moment we're constructing our knowledge about the surfaces from the given geometries, so that we are deleting all information and then adding the information again by comparing to the given geometries. Which is of course not an ideal solution, but it turned out to be a solution for the moment.
Okay, sorry, please go ahead. Sorry.
I understood that the problem was solved.
The problem turned out to be solved for a while when maybe I explained with a drawing it. Thank you very much. So, thanks, thank you. The problem is that when we've got our original domain and we put something in, and that was the case I tested, that does not modify these conditions that were originally outside, these ones, then it is well possible, if also these are split, that we can separate, these are the old ones, and these are the newly generated ones. But however, once one does something like having the volume that is removed from the mesh and the boundary, these conditions here seem to cause the problems, because here it is hard for the algorithm, if the geometry is not really exact, or the distance field is not entirely exact here, to know which one is the old one and which is already the new one. So once we have this situation, unfortunately, the problems still continue.
But the ones that are on the bottom, are they marked correctly or not?
These ones here?
Yes.
Until this point, yes. And once this transition appears between old ones and new ones, here, as far as I understood it, here the problem occurs.
But the old ones are supposed to be stored in a color map, so you are supposed to know the old ones where it belongs in the image should model pair and so on. And the new ones are supposed to not belong to anything. That was like very clear to follow. It's like
Exactly.
So you are supposed to distinguish between them, or even that way they are repeated nodes and they are coinciding, and that's a problem.
The problem is exactly, you're right, from the theoretical understanding, that's also what we had. The problem is that at some point a null pointer is returned to a condition that somehow was lost. And this is at the moment a simply technical problem, in my opinion, that we do not know where this null pointer comes from and why it is there.
No, because sometimes there are errors in the library. For example, when Ricardo found an error, we posted in the forum and they fixed it because it was just a technical error, was a super stupid thing. And sometimes it's like, oh, I am doing something wrong, and sometimes they did something wrong. So that's why I need that minimum example to try to find the reason, and if not possible, just to say, I think you have a problem, or you have an error. That's
okay. That would be clearly one approach. Unfortunately, we first of all tried this one with the bone inside, and here it worked nicely. That's why I was of the opinion for a while that this was working nicely, and then we went back to trying something like that, because unfortunately this minimal example led us to the wrong conclusion that things were working. So the problem actually turned out to be here in the transition between newly generated and old and marked conditions. Okay, this being said, any further questions?
no.
Then at this point we start into the second part of the coffee talk, which begins with the introduction of our newly implemented two-fluid Navier-Stokes solver. So what were the objectives behind this implementation? We wanted to have a solver which is able to handle a wide range of root numbers, that is able to resolve three-dimensional flow features, and that also can deal with violent surface motion, as we see in this stilling basin here at the bottom. Finally, our implementation is the 3D Navier-Stokes, solves the 3D Navier-Stokes equation, both for the fluid 1, for example the water, and for the second fluid, which is the air. We have a very robust mechanism for the capturing of the free surface, which is based on the level set approach. Finally, we employ a locally enriched finite element formulation, which is able to resolve the discontinuous pressure gradient at the surface and thus maintain a smooth surface even at low root number flows. Around this solver, several implementations have been done in Kratos during the last month. We put this solver into NBI. We employed NBI parallelism, not only for the solver, but also for its auxiliary components. Among these auxiliary components, we find an approach which is responsible for the mass conservation. One approach would be to apply a global correction, whereas we've also got the option to correct locally. An inlet process was added, which gives the user the flexibility to set a certain level for the interface at the inlet, but also to assign different settings for the fluid 1 and the fluid 2, meaning for the air and for the water in our application cases. Also, it is possible that the inlet conditions vary over space and time. For example, we can assign a velocity profile, or we can control the volume flux over time. For example, we can let it decrease. Further on, we extended the slip condition a little bit. We had the problem that particularly in hydrostatic cases, unphysical flow patterns were appearing due to surface tangential components in the residual. This was eliminated, and we also got now the option to apply a Navier slip condition to simulate the effect of a wall friction. A first validation study was done on different benchmark cases, for example the dam brake case, but we also simulated the flow over different structures from hydraulic engineering, like weirs. But now let us go a little bit into detail of the level set approach. The main feature, or one of the main features of this solver is that it is able to capture a sharp interface between the two fluids. In this example case, we simply want to convect this bubble of fluid 1 carrying in the velocity field of fluid 2. In the level set technique, this is represented by a side distance field. The fluid 1 has got a negative distance value. The interface is exactly the zero level of this scalar function, and the fluid 2 is indicated by a positive distance value. Now we've got two processes going on. One is that the distance field, the scalar field, is convected by the velocity inside our fluid domain. The second one is that we maintain the distance property, the signed distance property of this function by a reinitialization procedure. Just to come back to the question before, this is also done by the variational distance process that more or less solves the equation, the gradient, the absolute of the gradient of the distance field is 1, the Iconian equation. Okay, these two components make our solver very robust because they allow us to represent topological changes in our fluid field. For example, splashes can separate from the fluid, but we can also simulate topological merging between two fluid components. However, the level set approach also has got a shortcoming. One of the major shortcomings is the mass conservation. Here we implemented a correction mechanism which is more or less based on the knowledge about the theoretically expected volume of the fluids inside the domain. So we first of all compute the initial volumes, and we also keep track about the flows of volumes that cross the boundaries of our domain. Knowing what amount of fluid we would expect inside our domain, we can now either say, okay, when we're missing fluid, we can shift our distance field on a global basis and add the missing volume everywhere around the surface. We soon found out that this has got a distortive effect, especially when our mass losses are concentrated in one spot of the domain. Thus, we came up with a more local approach. In the local approach, we consider the velocity field, which is present inside our fluid domain. And here we take into account that possibly our fluid, the losses of our fluid volume are situated in the places where we've got a velocity component that is normal to our interface. So in a hydrostatic case, we don't have losses, we don't do corrections, whereas when we've got violent surface motion, where we are more likely to lose mass, we are going for the correction. Including this correction procedure into the algorithm leads us to the following procedure. We correct the level set, we reinitialize it, we assign the physical properties of our two fluids. From this point on, we can solve the Navier-Stokes equation, and we do the mass conservation based on the knowledge about the new velocity and pressure field. Once we are talking about the solution of the Navier-Stokes equation, we should also mention the speciality which comes from the element formulation. This two-fluid element was motivated from the following observation. When we've got two fluids with a different density in a hydrostatic case, we've got the following pressure distribution. And we've got this kink here in our pressure distribution. That means we've got a weak discontinuity in the pressure field. It is not possible to capture the discontinuity, or the discontinuity of the gradient, of course, with the shape functions of a regular finite element. Thus, the following trick is employed. It is a local enrichment of the pressure shape functions. The procedure is now the following. We iterate over all elements. We analyze the distance field, and once we see, okay, the element has got positive nodes with a positive distance on the one hand side, and with negative distance values on the other hand, we know, okay, this element is cut by the interface. We now split the element along the exact position of the interface, which we can also retrieve from the distance information. Now we introduce the additional local degrees of freedom for the pressure enrichment. Here, these shape functions come into play, which have got a discontinuity along the position of the interface. To maintain an accurate numerical integration, we perform the numerical integration on the parts of the element, so that the effect of the splitting is not neglected by an overall integration. Now we can get rid of our additional local degrees of freedom by a static condensation, so that the actual and final contribution of the element to the assembled system is exactly the same as it would be for an element that was not enriched and not cut by the interface. Now that we've a rough understanding of the solver itself, let us apply it to some cases in hydraulic engineering. We decided to do some simulation of weirs. Why are weirs, or measurement weirs to be more precise, so interesting? Well, at first glance they appear boring. But the reason is the following. We've got a transition from a slow water flow in subcritical conditions to a place where the flow has got supercritical conditions. Also, we want to simulate that this nap is detaching from the structure. Apart from that, we have, of course, a very violent surface motion in the stilling basin, which is downstream of our weir. So with all these aspects being considered, the weir seems to be quite an interesting case. Here we've got the Reebok weir, which is a thin plate weir with a thin crest and just a horizontal crest. Thus it can be simulated in 2D if we take into account that we need to take care of the aeration of the rear body. Here the air can come in through this at this place, whereas we need to establish an outlet condition in our simulation here, such that no under pressure develops in this place, which draws the nap towards the structure. Once we consider this, we experience a good agreement with the formula of Polanyi, which is commonly used to compute the discharge over such a weir structure. In the next case, we are investigating the Thomson weir. Here, the discharge happens over a V-notch in the weir body. Thus, we also have to resort to a three-dimensional approach for our numerical simulation. We've done this also for different levels of our spatial resolution, and we found that even though there is a factor of more than 10 in the number of the elements used in this simulation, even the causes of them is able to simulate the basic features of the flow, which is a very important thing for us because we won't be able to go for this very refinement in our large-scale simulations of the natural environment, of course. On the other hand, we also need to consider that, of course, that the very small and filigree flow structures can, of course, only be represented in the finest resolution. Also for the Thomson weir, we observe a good agreement with the semi-empirical formula that we have here. Now, let us leave the laboratory scale and move to the large scales which are present in the natural environment. Here we want to simulate a discharge event in a mountain torrent. Of course, there are several processes going on, like the transport of solids, also floating objects are present, but we would like to focus purely on the hydraulics of such a discharge event. Additionally to that, we also want to include the effect of mitigation structures, like for example the check dams that we see in this figure here. We follow the pipeline that has been presented by Nicola by first of all extracting the torrent valley from our geodata set. In order not to waste computational resources, we want to do this quite exactly. In the next step, we produce the volume mesh, here already in its remeshed form with a quite high quality mesh. As a third step, we then include the structures, like for example the jack dam, as you see in the picture at the bottom. Now, let us start in with the first simulation. Here we've got a valley with a length of 100 meters. The data set that was used for this one had a horizontal resolution of roughly 1 meter, whereas the height of the terrain is represented up to an accuracy of 10 to 20 centimeters. The simulation that you see here was run on 84 processors, and it took around 2 hours to solve for 700,000 elements over 900 time steps. Particularly where the water is very shallow, the effect of the mass conservation processes becomes evident, because otherwise we observe that if the spatial resolution is not fine enough, the water stops somewhere in the middle when it becomes too shallow. Now we jump on to a further simulation where we already included a jack dam. This structure here in the middle. The domain size was decreased to roughly the half of the previous one, and we now use a finer spatial discretization, which brings us an overall mesh size of 1.5 million elements. If I make a map and in this case we observe the effect of the refinement that Nicola described. If we're doing it without the refinement, the counter of our check dam will never have these sharp corners, and the flow does not detach as we expect it to. Thus, the refinement around the zero level is very important for such cases with sharp corners. A further thing that our pipeline is able to do is to perform changes to the topology of the domain, as we showed with this ball. So here we took the chance to introduce a bridge over our torrent, and also to, well, include something like a slice in the torrent. Of course, from an hydraulic engineering point of view, this is a pure nonsense to do such a thing, but please only consider it an example for the application of the pipeline. Here we see that also for that case, our mesh had a sufficient quality to simulate the two fluid flow. From the top view on this domain, we see that we depict, or that we represent, a lot of three-dimensional flow features. And these flow features, of course, would never be able to be there if we only used a shallow water depth integrated flow. So in such case, it is our solver really shows its big advantages over surely computationally more efficient shallow water applications. But this is the case for three-dimensional terrain with really steep gradients. Okay, as I think we've now nearly reached our end, but we still like to add our outlook, right?
Yeah. About the wind simulation, the idea is to compute is to couple a weather forecasting code with a CFD code, where the output of the forecasting code become the boundary condition for the CFD code. And with this CFD analysis of wind, we can perform an accurate evaluation of building energetic performance for the new building or old building, new buildings, or for the existing buildings. So this is the main idea in this topic.
Also from the hydraulic engineering perspective, there are quite a lot of interesting things left to do. For example, particularly for these torrent flows, it would be interesting to have boundary conditions which can represent the very high roughness of the surface. Of course, we've got rocks around, we've got debris laying around, so that would be interesting. Even more interesting would be that this roughness information is extracted in an automatized fashion. For example, out of airborne imaging, where we could use multiple color spectra to analyze the surface. A further application would be to use different material laws, for example, to simulate debris flow or mud flow in torrents. These are all flow-like landslide movements, and we would need a Bingham material model, for example. Also the cross-fluid and the cross-biological model is used in these cases. But I think the main part is to really validate these parameters. The material models are there, but the validation point is probably a huge challenge. Also, the coupling with the solid transport processes could be interesting. For example, one could simulate the transport of the bed load, these rocks that are transported along the torrent, but also floating objects, like, for example, wood, pose danger to bridges, and thus a simulation of these floating objects could also enhance the real-world use of our two-fluid solver. We thank you for your interest, and before we come to the very, very end, we would like to use the chance to thank our two supervisors that have accompanied us on our trip through our geo pipeline and through the wind simulation and through the water simulation. Ricardo Rossi, Professor Ricardo Rossi, and Dr. Ruben Surya. Thank you very much, and also, of course, thank you everybody for your interest in the
Short one.
Yes.
The boundary condition with the bed is a no-sleep or sleep condition right now?
At the moment, it is a mixture between both. To be more precise, it's a Robin boundary condition. We're using the, well, I think it is not so short as you would expect it to. But the problem with we would actually like to apply a no-slip boundary condition. But then we've experienced the problem that our level set function is not convected at the nodes which are here and which are no-slip. So in fact we would then observe something like that, where we've still got here dry and the water forming a very unnatural shape around the floor. The flow behavior more looks like the flow of honey or of an oil than of water. On the other hand, when we apply a slip boundary condition, our flow tends to accelerate enormously down these valleys and we get velocities which are unphysical, purely unphysical and unrealistic. Now the combination between both is this Navier-Stokes condition, where we say that we apply a certain tau, a certain friction here, a stress, which is a function of the velocity at the bottom node. So that this compensates for the friction that would actually be there from the bed. Thus we can combine both the frictional effect, but also we've now got a natural waterfront without having these strange honey-like flow behavior. Sorry for making such a long one out of a short one.
Well, Ricardo was pointing out that, well, as you know, some time ago, what I wanted to do is to couple this with the DEM, because we want. However, the task of doing that has gotten longer than I expected, because I had to change a lot of things from DEM and from swimming DEM, because they were very far away from the fluid dynamics scheme of things. Luckily, now we're getting closer, so I hope that in the future you can just place a few rocks, DEM rocks there, or logs, for example, as you say, and couple them to the fluid. I think that wouldn't be difficult.
That would be great and truly enhance the use of such an application.
I have a question, and that's a question I repeat. So I asked you last week, so what is missing in order to really be able to use this? I mean, for the pipeline to really work robustly, I understand that there are still things to do. I understand that one is the MLG, let's say it is, or our interface to MLG, whatever. What are still the road blockers, let's say? You're on camera, you must be true.
No, for my topic, up now, the pipeline worked very well, but I need to improve some stuff, so at the moment it works very well. But after I need to do other stuff. So.
Well, and about the budget conditions, I'm sorry.
Just let him answer. I'm curious to see what is still not working. Sorry, it's
If I may quickly, adding a point here. Of course, it's this MMG-related thing, and we also don't have a test yet for a real-world scalability of this. For example, of a town containing 50,000 buildings, we had hoped that we could present the scalability up to a village size so far, but we cannot extrapolate how it would behave if we've got, for example, the whole town, including over 10,000 buildings, where of course the mesh size is very large, and whether then the performance can be maintained, since we do not have an API application yet.
You don't have an API application?
No, no, not for the meshing, not for the meshing.
Not for the meshing. So the bottleneck is the mesh generation of the first step, let's say.
I'm sorry?
The bottleneck is in the initial pipeline, not in the solve right now.
Exactly, in the meshing of the terrain model. So we've invested some thought into this, that for example, we can do one building after another. So we do one, then we refine the mesh for the next one, so that they can be put in a sequential fashion. One is being generated after the other. But you can imagine that here, of course, after every building, we add additional cells. So that this is still becoming large. And of course, then the operation for the next building is always getting more and more expensive. And whether this really can scale up to a big town like Barcelona or Munich or something like that, that is still not tested for our application so far.
Okay.
Okay, I'm sorry.
Sorry.
Okay, no, I didn't realize that you were still answering. And the boundary conditions, are you relating those to any physical parameters of the river bed, for example, or?
Not yet.
But it can be done, I guess.
It could be done. It surely needs some calibration. What we did so far is that we iterated to gain this torque, this stress here, from the log law. So that we simply said, okay, we assume a y plus of 70, for example, and then we iterate to get it from here. Of course, in this log law, we can now put in a parameter that represents the roughness. But that also just works to a certain extent. So the main assumption is that it's below most, the value I found in literature is 10% of the boundary layer size. Of course, a rock that is inside such a torrent is larger than these 10%, and we really need to put this object into our domain representation. So this is a scale problem. You always need to consider how much scale things, or how
You
much
model and how much you...
exactly.
And the other question was related to, I forgot, 1 second. Oh yeah, and what are the physical effects that you still think need more modeling? For example, to get a very an accurate representation, if you had to rank the physical effects that you are simplifying,
Okay.
what are the most important? Would it be, like, for example, turbulence modeling, or that is well captured, or perhaps air entrapment?
That would truly be the case. For example, we tried to simulate a hydraulic jump. In this case, we cannot predict. It forms something that looks like a hydraulic jump, but still the dissipation is way underestimated. So the air entrainment would truly be one aspect, but most of all, what I consider most critical is still the friction on these terrain surfaces. Also taking then this effect to the further material models, where it's possibly even more complicated to model it.
Silenzio sepulcral. So, shall we